Section 7.4 is called definition of a reactive source and a reactive load. So, if this reactive power is flowing, it's received and then it's delivered back, right? So, how do we, define that? I mean, because it really matters, at one point it's received it and the other part it's returned it. So how do you define that to be able to work with it? All right. So the way that we do that, we simply define something called a reactive source and reactive load. And what we're going to find out for this inductive element is it is defined as a reactive load. Okay. And so the generator supplies the reactive power, and the inductor absorbs reactive power. Let's look at an example of this. We're actually going to put some real numbers with this now and some values and do some calculations with this. Here's a circuit, has a source of AC here. And what we're looking at is the effective value of 120 volts out. And that is delivered to this inductive load, which we sometimes call a reactor. 120 volts, 30 amps. I sub L is current to the inductor. We have that representation of that, but we can also know now that this is reactive power and it's represented by this letter Q. And so by definition, a reactor or inductor, as we've always thought of it, reactor, I'm going to write that down. Reactor is an inductor, it's the same thing, but the reactor is considered to be an reactive load. So this is a reactive load, okay, because it absorbs reactive power. This would be our source of the reactive power. Now, a source can supply active power or reactive power. It depends on what the load is out here. So now we've got some values and a problem to work in example 7.2. Let me clean this up right quick and we'll just work this problem. And you're going to be working on advanced topics, and at the same time, you're going to be just amazed at how easy it is. He says, first off, calculate the value of the current in the reactor. Okay, so he's already given us a value here, which we didn't have to calculate, but that is 4. And if we needed to know the angle, that would be 4 at 90 degrees, but we don't even need to do that. And if we wanted to put it in an equation, we would put it in as J4, right? And we know that that's an inductor. But we don't even have to do that. It's even easier than that. All we have to know is it's 4 ohms of inductive reactance. And current is equal to voltage divided by resistance, but it's not in resistance anymore, right? It's an impedance, and that value happens to be, it's a, Z. And so that value happens to be the voltage divided by 4. Let me put some numbers in here. The voltage of 120 volts, 120 divided by 4, which equals 30 amps. So 120 volts supplied to this 4 ohm inductor, 4 ohms of inductive reactance gives us 30 amps of current. Calculate the power associated with that. I know, its power is equal to voltage times current. Power is 120 volts, current is 30 amps, and I'm going to write that down, and I'm going to come up with 3,600 watts. 3,600 watts. Oh, but I'm not dealing with resistors anymore, right? So it's not watts. It's an inductive reactive power. So I have to change that, and I have to recognize that that is VAR, volt amps reactive. And so I want to write this like he has it, which is 3.6 kVAR, kilovolt. All right. So we calculated the power. Then he says, calculate the power associated with the AC generator. Calculate the power associated with the AC generator. He says, because the reactor absorbs 3600 VAR or 3.6 kVAR, the AC generator has to be the thing that's supplying it. Consequently, the generator is a source. The generator is the source of reactive power, Q, and it is delivering 3.6 kVAR to this reactive load. It's the only thing it could be, right? It's all about definitions. And then the phasor diagram for this, since this is purely inductive, you know, and these are drawn to scale, right? But we see that since this is purely inductive, there's a 90-degree phase angle between the voltage and the current. The voltage leads the current by 90 degrees, and we've shown that. And so I think that's it. The phasor diagram applies to the reactive load and the reactive source, as well as the line that connects them. All right. A real circuit with some real things and some easy calculations.